Hello everyone, this is my third video on MATLAB, and the main objective of this video would be to plot a simple function y is equal to x squared in MATLAB, and we would be plotting it between x is equal to 1 and x is equal to 5. There are a few sub-objectives, so the sub-objectives are to explain to you the features of the plot function, how the plot function works, and the linspace function, which will come in really handy later on. So let's start. So I assume all of you are familiar with plotting in Excel. So for example, if you wanted to plot y is equal to x squared in Excel, so you would select five x values, for example, 1, 2, 3, 4, and 5, square them. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And then what you would do is select these and then go to insert and click on scatter chart, for example. So you now have a pretty neat plot of y is equal to x squared. So to do the same thing in MATLAB, we would have to store the x values in an array, the fx values in another array, and then relate those two arrays together to have a one-to-one correspondence. We have to um, make MATLAB understand that 1 relates to 1, 2 relates to 4, 3 relates to 9, 4 relates to 16, and 5 relates to 25. So let's start off in MATLAB. So in MATLAB, we would have to first um, store the values of x in an array. So we declare an array x is equal to 1, we give a space bar, then 2 space bar, 3 space bar, 4 space 5. So you now have the x values. Okay, so now you have to store the fx values. So y is equal to 1 square, which is 1, 2 square, which is 4, 3 square, which is 9, 4 square, which is 16, 5 square, which is 25. So yes, so we now have x and y stored as two separate arrays, and then we have to use the plot function. So we write plot x comma y and press enter. So as you can see, we have um, plotted y is equal to x squared. Um, this is the plot in MATLAB. As you can see, it's pretty coarse, and we will see how to make it more um, finer. You can do that by adding more x values between 1 and 5. For example, if you uh, put in a 1.5 here, 2.5, 3.5, 4.5, I'll be coming to that. You don't have to do that manually. Actually, there's a simpler way of doing that. um, I mean, you could just uh, write x is equal to 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 5. Okay, and then you'll have to square these values. So instead of manually entering the x square values as I entered in the just before this, so I actually entered 1, 4, 9, 16, 25 manually without instructing the computer to do so. So if I want the computer to do the squaring for myself, So I just do y is equal to um, x dot to the power of 2. So the dot is very important here. Do not miss this. Um, so okay, so I press enter. So now I get now each of these x values have been squared. So 1 square is 1, 1.5 square is 2.25, 2 square is 4, 2.45 square is 6.25, and so on. So we again use the plot function, plot x, y. So you see the curve has become much smoother than before because there are many more points, many more pairs of x and y. And obviously, as you increase the number of points, the curve will just become smoother and smoother. So there's another thing I wanted to show you, which is the properties of the plot function. So here we have uh, the x values and the y values stored in the um, separate arrays. So what the plot function does is links the first element of x to the first element of y, the second element of x to the second element of y. Okay, so plot recognizes that this is related to this and not this. Okay, so the square of 1.5 is 2.25 and not 4. Okay, so it links the second element to the second element in both of these arrays, the third element in x to the third element in y. So it assumes that the third element of x and the third element of y are related. So it assumes that these are pairs of x and y's. Okay, and there's another interesting thing. Um, that is, if you jumble up these pairs, for example, instead of writing x is equal to 1, 2, 3, 4, 5 and doing y is equal to x dot to the power of 2 and doing plot x y. Okay, this is the standard convention that we use while plotting. But what if we jumble these up? Okay, so instead of 1, 2, 3, 4, 5, we for instance write it as 2, 3, 5, 4, 5, 4, 1. Okay, so we've used the same x values, but they're in a different order now. Okay, so 2, 1, 2, 3, 4, 5. So it's the same digits that we used in the previous um, um, example, but but the difference is that they're not in the right order right now. Okay, they're in a different order. So let's see what happens. So we square all these values. So we write y is equal to x dot to the power of 2. So 2 squared is 4, 3 squared is 9, 5 squared is 25, 4 squared is 16, 1 squared is 1. Okay, so now if we uh, um, write the command plot x, y, will it be, will it give us the same result as we get in this um, example, the previous example? Um, it actually will not give the same result. Let's see what happens. Okay, so this is a very illegible plot. It's pretty different from what we saw before. So what happens is MATLAB starts from the point 2 comma 4. It assumes this to be the first point, okay, and then connects 2 comma 4 to 3 comma 9. Okay, so we start from, this is the first point, 2 comma 4. Then it connects 2 comma 4 to 3 comma 9, okay, the second point here. And then it connects 3 comma 9 to 5 comma 25, okay, and then connects 5 comma 25 to 416, which is somewhere around here, okay, 416, and then it goes back to 1 comma 1, okay. So the order is very important here. um, the order of you have to instruct MATLAB uh, that show MATLAB that this is the connectivity of my points. It's impossible for MATLAB to know the connectivity beforehand, so you have to show MATLAB that 1 comma 1 connects to 2 comma 4, 2 comma 4 connects to 3 comma 9, 3 comma 9 connects to 4 comma 16, and 4 comma 16 connects to 5 comma 25. So if we jumble the x's and y's, um, keeping the functionality the same, you just um, jumble the order in which it is written. MATLAB will think assume the first point to be 2 comma 4, and then go to the next point, and then it'll do as instructed. So this is a feature of the plot function. Um, let's take a look at linspace. Okay. So when I started with the example of the plot function, um, I wrote x is equal to 1, 2, 3, 4, 5. Okay, y is equal to x dot to the power of 2. Okay, and then plot x y. Okay, so we get the plot. What if we instead of manually entering x as in 1, 2, 3, 4, 5, what if we did not want to do this? I mean, what if we were just lazy and wanted the computer to do this for us? See, 1, 2, 3, 4, 5 is basically um, a series starting from 1 with a difference of 1 in between the numbers, okay? So there's a better way to do this. So there's a function called linspace, which which basically inserts numbers between two endpoints. The endpoints here are 1 and 5, okay? And the third number in this statement would be basically the number of elements you want to have in the array. So there are like 1, 2, 3, 4, 5 elements. So we write 5, okay? And then press enter. So instead of having to manually write 1, 2, 3, 4, and 5, we just write linspace 1 comma 5 comma 5. So for, let me give me another example. So assuming you want to write create an array which stores numbers between 1 and 10, and the total number of elements in the array is 10, including 1 and 10. So we write linspace 1 comma 10 comma 10. Okay, so we have the whole series from 1 to 10, okay, just by writing linspace 1, 10, and 10. So what if we want to enter more numbers? Okay, what if we want to enter a large number? Suppose we want to have like 20 numbers between 1 and 10. Okay, not between 1 and 10, including 1 and 10. So we write linspace 1, 10, 20. Okay, so see, So now we have 20 numbers including 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are 20 numbers um, including 1 and 10, okay, that we have generated. Okay, so so let's come back to our original example. So instead of 1, 2, 3, 4, and 5, um, x would be like linspace 1 comma 5 comma 5, okay, and y would be um, x square. Okay, so this would be a pretty coarse plot. Okay, so in the we previously saw that increasing the number of points would decrease the coarseness. uh, in this particular example, we manually entered 1.5, 2.5, 3.5, and 4.5 in between 1, 2, 3, 4, and 5. So we increase the number of points, number of x values, and obviously, yeah, the number of y values as well. And so we got a more finer plot. So uh, so in so we can do that in an even better fashion if we use linspace. So what linspace does is enters more numbers between the two endpoints, which is 1 and 5. You can enter as many numbers between 1 and 5 as you want. Okay, so if you want to enter maybe um, 10 numbers between 1 and 5, I mean including 1 and 5, so you write linspace. So we write x is equal to linspace 1 5 20. Okay, so you have an array of 20 numbers spanning from 1 to 5. um, so basically, and if you just square this array and plot it, you'll get a much finer um, graph compared to if you just plotted 1, 2, 3, 4, and 5. Okay, so using linspace allows you to enter a lot of numbers between um, 1 and 5, or any start and end point whatsoever. Okay, so y is equal to x square. Okay, and then plot x y. So this is a much finer plot than we got previously. Um, yes, so that's it for today.